Hello friends, thank you very much for watching my earlier videos on special theory of relativity. Now, in this video, I will be talking about general theory of relativity and interesting concepts connected to the general theory of relativity I will be discussing here. And already a study material has been prepared in this direction. Now, in general theory of relativity, we should know what are the consequences of general theory of relativity, why they are so interesting and exciting in this century. Main difference between special theory of relativity and general theory of relativity is, in special theory of relativity, we'll be talking the theory connected only to inertial frames of references. Whereas in the case of general theory of relativity, we'll be talking both for inertial frames of references as well as for non-inertial frames of references. That is why the meaning general. General means it has, Albert Einstein has generalized. His theory can be applied both for inertial and non-inertial reference frames. Now here we'll have one small concept regarding the modern gravitational theory. General theory of relativity is also known as modern gravitational theory. Reason for this is Albert Einstein has improvised the understanding of gravitation concept that was introduced by Newton in 1642 and later on. Newton had only the idea of gravitation, but the cause of gravitation, details of gravitation was not known to Newton. Albert Einstein, he could give more information about the gravitation, and hence general theory of relativity is also known as modern gravitational theory. Now, let us see one small example connected to this. I said in the beginning, general theory of relativity can be applied to both inertial as well as non-inertial frames of references. Let us say there is a lift and a person is standing here. Now, lift, when it is at rest, its acceleration is 0. But on the lift, acceleration due to gravity will be acting on it. Now, when lift starts moving either upward direction or downward direction, it will get acceleration value. Now, lift has got acceleration and acceleration due to gravity is also there, which is acting on the lift. Now, since lift is moving with certain acceleration, that is accelerated frame of reference. Now, if the lift is moving up, the person who is here, he will experience G plus A. If you want to calculate what is his weight, then I have to apply W is equal to M, mass of his body, plus G plus A for the lift moving up. When the lift is going down, then I have to calculate M, G minus A. Because G and A both are vector quantities, they are in the opposite direction. So G minus A I have to take. Now, the question here is, the person who is in the lift, when it is closed everywhere, he cannot make out what is acting on him, whether small g is acting on him or the A is acting on him. He is not in a position to distinguish it. So that is why it is known as a thought experiment connected to general theory of relativity, where we need to find out what is the G effect here in an accelerated frame of reference. For that, a lot of mathematics has been done, and then we'll be it's beyond our scope in this lecture to talk about the mathematics of it, but we can make outline of the important predictions which took place when we start thinking about the gravitation of a body, what is its effects on other things. And this concept, what we are talking here about the lift, is known as principle of equivalence. That means we are not in a position to distinguish between small g and A, and this is actually the second postulate of the general theory of relativity. Now we will come to the concept of the total. There are 4 concepts which are related to the general theory of relativity, very interesting ideas. Now we will see here, and they are practically also, all these things have been observed by the experiments, though the experiments are very not easy to realize, but complicated experiments, and we will try to make it as simple as possible, those concepts. The first concept is connected to curvature of space-time. What is this curvature of space-time? Curvature of space-time can be demonstrated by taking one simple gadget. Let us say I have got here a small gadget here. On this, I have covered this with a handkerchief. Now you assume that this surface is like a space surface, imaginary space surface. On that space surface, let us also think there are lines, vertical lines, horizontal lines. It is known as grid on the space. So there is a space, flat surface. On that there are lines. Okay. Now in this space, now if I put a massive object like sun. Sun is a star. Now let us assume that it is a sun. Now if I place this sun into this space, right? Now you see what is happening. What is happening is that flat surface has become now a curved surface. Curved surface. So in the space itself is becoming a curved surface. Now in this curved surface, I will redraw this diagram once again here, and we will see what we can understand from this. Now this curved surface can be drawn here like this. Initially the surface was like this. Surface was like this. Now because of an object, these horizontal lines, whatever are there, these horizontal lines have taken a bend like this. And this lines, because I have put the object here. So now this is sun. Because of the sun, the surface itself is becoming a curved surface. That is known as curvature space time. Now I am coming back to this gravitational concept now. Now what is this gravitation, how it is connected to this? Now this surface I can imagine to be like this. Now the curved surface is like this, right? Now at the center you have got a sun. Because of the sun, the surface has become like this. Now around the sun, now let us say this is a small marble is here. Let us consider this is a planet or Earth. Now if I place this planet here, right? Now what is happening now? It is going into a circular orbit around the sun, and it is because it is in the attraction of this gravitation, because this surface itself has become a curved surface, it has to go near to the sun only. And this is curved space-time concept of GTR explains how gravitation is working, how the gravitation attraction between the sun and the earth or sun and the other planets exist. Now let us get into the second concept, bending of light. Second concept, bending of light, connected to gravitational bending of light. What is gravitational bending of light? Let us see here. Gravitational bending of light. In this, let us say there is sun. Okay. Now, and I am standing here on the earth, and I am watching a star which is present here. Let us say for me, if there is a star, there is a star, from the other light is coming like this to me. I am thinking it is coming straight like this, but actually the star position is here. Star position is here, and this light is actually, it is coming towards the sun, and then it is taking this path. Because of sun's gravity, sun's gravitation, this light is getting bent here and it is reaching me. So actual position of the star is this, and I am thinking the star is present here. This is known as bending of light. According to Newton's work earlier, we used to say that light always travels in straight paths. Now when we understand more and more about the gravitation concept, then we can understand that light doesn't go in straight paths. There is a bending due to the gravitation also. Now this concept can be extended to a concept known as gravitational lensing. Gravitational lensing. What is this gravitational lensing? It's a very, very exciting field. Many galaxies have been studied by using this concept, gravitational lensing. Now, let us see here. This is already convex lens. Now, you can see this. Now, when you look through this, whatever I have written here, you can see the magnified picture in this lens. It's a convex lens. Object is here. On this side, you are able to see the magnified picture. Now, I'll replace this lens with a galaxy here, very big galaxy here, and this galaxy has got lot of gravitational force, and behind this galaxy, at far off distance, let us say there is another galaxy. Now that galaxy light coming from that galaxy will pass through this galaxy, and then final image you can see on this side. I will draw the diagram here. Let us say this is the massive galaxy. This can also be called as cluster of galaxies. Cluster of galaxies. That means there are many galaxies. So I am standing here on the Earth, and there is one galaxy here. There is one galaxy here. My aim is to study this galaxy. I have got a telescope. Through this, I want to see this. Now, here, whatever lens I used earlier, this lens is here. Actually, there is no lens. Here it's a cluster of galaxy which will act like a lens now, because light coming from here, it will bend like this. Light coming from here, it will bend like this. So, whatever this lens did here, if the lens position is here, light is falling on this, and then it will get focused here. So, we can see it here. Same lens, whatever this glass lens is doing, this cluster of galaxies are doing like working like a lens because of gravitation here. Here it is because of refraction. Here it is because of gravitation. So that is known as bending of light. That is also known as gravitational lensing. This concept. Very interesting concept, very exciting concept, because you are seeing something which you did not believe earlier. And this has been done. Many experiments have been done. Many experiments are still going on. Astrophysicists, astronomers, they are doing these experiments, and many new things are being found out every day because of this concept. Now we will talk about gravitational redshift. You have heard about Doppler shift. Doppler shift means if there is an observer and there is an object. There is an object. Like this object can be a star. Can be a star. An observer. And he is looking through the telescope, let us say. If the object is moving, let us assume, towards this, then you know that there will be change in frequency of the light as you observe here. So, when the object is moving relative to the observer, you can see the Doppler shift. Correct? And suppose if the object is moving away, depending upon the movement direction, you can have the value of nu, right? If it is coming near to you, the frequency will increase. Frequency will increase. Lambda will reduce. When the lambda reduces, it will be a blue shift. If the star is going away, then the frequency will reduce. When the frequency reduces, lambda will increase. When lambda increases, you have got a red shift, because wavelength increases means it is towards the red wavelengths. Now, what this GTR is doing here now? Gravitational redshift means because of the gravity, there is change in mass of the light. Relativistic mass you are getting now. Now, because of relativistic mass, what is happening here? C is anyway constant. According to special theory of relativity, C is constant. And relativistic mass is changing and h is constant. So if mass is changing means what is other quantity which can change? Frequency. So frequency will change now because of the massive gravitation available for the light to travel. So in addition to the Doppler shift, now you can have another shift, another change in the another value of change in the frequency nu. So once again you can see a gravitational redshift in addition to the Doppler shift you will see. So that we call it as gravitational redshift. Then fourth concept, Mercury orbit around the Sun. Now once again the gravitation concept now, whatever we are talking now because of the general theory of relativity, it has got effects in the movement of planets around the Sun. Why it will have effect? Because Sun is a very massive body. Sun is a very massive object. Now its mass will be something like 6 into 10 to the power of 24 kgs. Very high mass. In our solar system, 99.8% is Sun only. Remaining 0.2% is other planets and all those things. So it is a very big object in our solar system. Now around the Sun, in the orbit you have got Mercury. Mercury planet is there. So Mercury planet is going around a very massive object. Just like in the beginning I told curvature space-time, there is a curvature. Sun is present. So in that curvature the Mercury is going. So when the Mercury is going around it, its path, generally we think its path is like this. But actually because of the gravitational concept here, now its path will be something like this. If the Sun is present here, let us say Mercury's position was here earlier, it may come like this. Next it will go like this. Next it will go like this. So this is the original position of the Mercury, and it is now what is happening here is it is not tracing the same circular or elliptical path. There is a change in its plane. It is that ellipse itself is, we call it as wobbling ellipse. Ellipse itself is wobbling. So this is the Mercury orbit around the Sun. Now there is one more concept. There are many concepts connected to this. In the case, and many things have been tested. This has been Mercury thing, and the gravitational redshift and all these things have been checked with other stars like white dwarf stars and all. They have, gravitational bending has been checked, and they have even found out what is the angle. See, for example, you have got the Sun here, and then I said there is a bend here, there is a bend here, and here this angle, if you find out, it is 1.75 arc seconds. So that much angle they could see. Like that, experimental detections of the predictions of GTR have been found out, and still experiments are going on. It's very interesting concept. Thank you very much.